So if you're one of the people who's been really motivated to study calculus for practical applications, to try to optimize things in your life, in your business, in the world, this is what we're getting ready to do. That's what we're going to do next week. Today we're going to learn the technique of how to do that. So that's about finding extreme values. As we mentioned before, if you want to find the highest point on a graph or the lowest point on a graph, those are ways of finding the best way of doing something or the worst way of doing something. You want to be sure that you're finding the right one, and we'll talk about that later. So we're going to look at a few graphs here to illustrate what can happen about these extreme values, trying to find the high and low points on a graph. So here's our first example, and this is the entire domain of the function. So if this represented, say, the way of earning some money or something, and you wanted to try to earn the most money, then you would want to find this point up here, right? Use calculus to figure out where that point is, maybe by looking for where the slope is 0. And so this would be called the highest point on the entire graph. We call that a global maximum. It is the highest point in the entire universe, the entire world, for this graph. Do you see where the global minimum point is? The global minimum is down here. That is the lowest point the graph ever got to. And so again, depending on the situation, you might be interested in finding the global min or the global max. If this were, say, a graph that represented how much material it used to create a certain product, then you would want to find the least material. So that's the global minimum and maximum. We'll often just refer to them as max and min. So for example, if this were the planet, this would be the highest point on the whole planet. Maybe some of you watching at home live near there. I think it's Mount Everest, right? But those of us living in New England, we have our own highest point nearby, and we're proud of that. It's called Mount Washington. So for example, here, this point for us is a local maximum, meaning that in our neighborhood, and that's the official math language, believe it or not, in the little neighborhood, if I look at an open interval to the left and to the right, this is the highest point. So I've got to be sitting there. I can look down to the left, and I can look down to the right. So this is a local maximum. It's not the global maximum. This point is higher up. I probably should have drawn this one a little higher. This one is supposed to be higher, more easily seen higher up than that. But if you're sitting at the top of Mount Everest, you're also at a local maximum, right? So this is a local maximum and a global maximum here. Right? You might be sitting at the top of Mount Everest, and you might not know that you're the highest on the planet, but you're definitely still a local maximum. Do we have any local minimum points here? We've got one right here. If you're sitting at this point, when you look to the right or you look to the left, you look up. So this is a local minimum. And then there's the question about whether you ought to call these points local minima or not. And this is a matter of convention. Just like we talked about earlier, sometimes some books do include endpoints in the intervals, some books don't. It's really not an important question to worry yourselves about. My convention in this class is that endpoints of a graph cannot be local extrema. So our convention, and it is just a convention, we just have to decide something, endpoints cannot be local extrema. Of course, they can be global extrema. We see one right here. This is a global minimum, right? Endpoints cannot be local extrema. But again, an extrema, this is sort of, this is the way to say something plural properly. Like the plural of stadium, you're supposed to say stadia, not stadiums. So the plural of extremum is extrema. The plural of maximum is maxima. So this is going to be our convention in this class. But as I was saying, for example, the AP calculus people, they will not ever ask a question where you need to decide whether an endpoint is or is not a local maximum or minimum, because they know that different books teach it differently, and it's not an important question. All right, so there's one example. Now how about this example? Now the graph goes off forever to the left and the right, and it goes up forever and down forever. So what have we got here? This point is a what? This point is a local minimum. Is this point also the global minimum? Is it the lowest point that the graph ever gets to? No, right? The graph gets below this point, and then it keeps going down and down forever. So the question is there a global minimum for this graph? You might be tempted to say that the global minimum is way off to the left forever at negative infinity. But is negative infinity an actual point? Not in this class, it's not. So we say that there is no global minimum here. You're not allowed to say it's at negative infinity. It's got to be a point where you can actually put your finger on it. So what do we say about this point? This point is a local maximum. And is this point also the global maximum? No, it's not, right? Because we get higher than that point, but then the graph just keeps going up and up and up forever. And for the same reason that there was no global minimum, there is no global maximum either, because you might be tempted to say it's at positive infinity, but positive infinity is not a number. You can't put your finger on it, so we don't call it a global max. So let's start to keep track of what can happen. We can have a global max or a minimum at maximum or minimum at an endpoint. Right? Here was a global min at an endpoint, and here was a global min at a place that was also a local. This was a global max, a place that was also a local max. What do we got here? This point is definitely a what, and this point is definitely a what. They're definitely local minimum, local minima. That's a local minimum. That's a local minimum. This point is definitely a local maximum. What about a global minimum? These 2 points are both the lowest point that the graph ever reaches. So the question is whether we want to call them both global minima. So, for example, if in the company where you work, you and one other person both earn a certain salary and nobody earns a higher salary, are you justified in telling your grandmother that you have the highest salary in the company? Yes, you are, right? You have the highest salary. Somebody else has the same highest salary, but you do have the highest salary. Therefore, these are also both global minima. So it is possible to have more than one global max or min. For example, sine of x has how many global maxima? Infinitely many, right? It keeps hitting 1 and 1 and 1. What about a global max here? So the reason that we drew this graph with this vertical asymptote is if we just happen to look at this local max, you might think that this is the highest y value, but you have to pay attention to a vertical asymptote. So this y value is exceeded by all of these y values. Is there a particular x value where we get to the highest y value? A particular place you can put your finger? No. It just keeps going up and up and up. So for this one, we say no global maximum. So these are meant to illustrate to us all the different things that can happen, because our next job is going to be try to come up with a procedure for finding, using calculus, local extrema and global extrema. And here's our last example. We've got a what here? This is a global maximum. This is a what? Global minimum. And do we have any local maxima or local minima? Remember, our convention is that endpoints cannot be local extrema. So in this case, no local maximum, no local minimum. So the purpose of looking at these 4 graphs was to illustrate the various things that could happen, to help us now come up with a way to formulate a method for finding local extrema and global extrema. So that'll be in the next video segment, but please keep these pictures in mind or refer back to them when we're coming up with that procedure.